In this video, we're going to talk about parametric equations. So we're going to think of x and y as functions of a third variable. We'll call it t. This is known as a parameter. And so each t value is going to give an x and a y value, which if we think of the xy plane, that'll give us a point in the plane, x of t, y of t. And the collection of all those points as t varies is called a parametric curve. The equations x of t, y of t that define that curve are called parametric equations. Here's an example, and you can tell that y is not a function of x in this case. This is not the type of curve that we would see in pre-calculus or in most of the stuff we do in calculus. So we get a few more interesting pictures here. You can see the definitions of x and y involve sine and cosine in various ways. And in this animation, I actually have this plot sort of built one by one. So t is going to start at 0, and it's going to move up until it reaches pi. And when t gets to pi, it's actually going to end up back at where it started. So here it goes. As t increases, the function moves along. It kind of traces these out, and then gets back where it started. And if I let t keep going, it would just trace out the same curve again, and around and around and around. So parametric equations not only have a location, they're points, but a direction. As you think of t increasing, you can think of these points as moving along this path. By hand, you could graph these things with a table of values. You just choose a list of t's and then plug them into the xy function. Usually kind of tedious, so it's nice that Sage has a built-in command to handle this. It's called Parametric Plot. Looks like this, parametric underscore plot, and then parentheses. And then what you feed it is an ordered pair, so another parentheses, and x of t comma y of t, which you need to previously define, the x and y functions. And then a comma, and this thing tells it what t values to use. Of course, it doesn't have to be t. You can define x and y as a function of w or whatever. This specifies the variable. This is where your variable is going to start, and this is where the variable is going to stop. And you can change that, of course. There's a toy called the spirograph, which I put a link here to the Wikipedia page about spirographs if you've never seen one. Has collection of various sizes of wheels that you stick a pencil in little holes, and then you move the wheels around, and as they move around each other, it traces out strange looking curves. And we can actually produce spirograph kind of pictures using parametric equations in Sage. So I made this little interactive box. This is a and b are a couple different constants that show up in the equations. You can see where the equations are here. There's the difference of a and b times cosine plus b times the cosine of a minus b over b, and then multiplied by t, and then y is similar but with sine. And so kind of a strange mixture of these numbers a and b, and they do interesting things to the picture. Here is a is 5 and b is 2, sort of like choosing different sizes of wheels in your spirograph toy. We get this 5-pointed star here. If we change a to 7, then this thing has 7 points, and if we do 9, we'll get 9 points, and so on. Now if you choose even numbers, then when a is even and b is even, there's some sort of cancellation that goes on in there, and so now here we actually only get 3 points to that. If we change b, oh, that was a degenerate case, looks like, so maybe that was not a good choice. Alright, b is 4 looks pretty much like b is 2. How about 5? Okay, so now 6 and 5 don't have common factors, so we get 6 points, though not really a star anymore. So that's one thing you can do. Let's change this b back to 2, and I'm going to put this a at a half now. And we get this fraction, a very different kind of shape, sort of this circle within a circle. This thing is almost like a little heart-looking thing. So you can play around with different things there. Now let me finally do an irrational number. I'll put the square root of 2 in there, and I'm going to, it starts here, and it starts tracing around, bounce, 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 and it keeps bouncing around, and I haven't gone far enough. I'm going to have to increase this I'll go ahead and put it at 100 pi. What happens with square root of 2 is it bounces around. It never quite gets back to where it started. Like when you had a whole number, eventually it goes around, it gets back to the starting point and repeats. Here it doesn't quite repeat, so it starts, maybe here and it bounces around, but it doesn't end up here again. See, it's a little bit off. It jumps over the starting point, ends up here, bounce, 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 and so it just keeps getting shifted a little bit each time. And let's increase the number. So T max just increases how many points it's going to do, how many times it goes around. Now these lines across here I think are probably errors just due to rounding, so kind of ignore those. But as this bounces around, it starts filling in more and more and more of this, kind of makes a filled in donut here. So I'll let you play around with that, interact different kind of values of A and B and see what kind of different shapes you can make. Of course, we don't want to just graph these things. This is a calculus class, so we want to do some calculus. We want to find slopes of curves and draw tangent lines, stuff like that. So in this example, we're going to consider x of t is 2 times the sine of 2t, and y is 2 times the sine of t. And here's the graph. Now you can tell y is not a function of x. It doesn't pass the vertical line test. But if you look at any point here, it looks like there should be a tangent line there, or over here there should be a tangent line there. So it seems like this curve has slope even if y isn't a function of x. It's sort of perhaps a couple functions of x glued together. Well, maybe more than a couple, several functions of x glued together. So let's go ahead and try to find out how we can find the slope. The way we're going to do that is with the chain rule. So I'm after dy dx, and the chain rule says that if y is a function of x and x is a function of t, the derivative of y with respect to t is equal to the derivative of y with respect to x times the derivative of x with respect to t. And as long as the dx dt is not 0, we can solve that for dy dx. Just divide both sides by the derivative of x with respect to t, and we get this relationship. So the derivative of y with respect to x, which is the slope of the curve in that graph up above, is the derivative of y with respect to t divided by the derivative of x with respect to t. Or think of it this way, y prime over x prime. If you think of those as functions of t, these primes are derivatives with respect to t. That means we found the derivative of y with respect to x as a function of t, not as a function of x or y or both, but a function of t. So if I give you a particular point in the xy plane, so some xy point, in order to find the slope there, we need to know the t values that give us that point so that we can calculate this. Alright, in this example, I'm going to find the tangent line when t is pi over 6. So t is given here. I didn't give you x and y, I just gave you t. So we want to get the tangent line. So I need three things, the x-coordinate, the y-coordinate, and the slope. So let's find the slope first. So I defined my functions x and y, same ones I used up to graph above. And now the slope is the derivative, dy dx, which I just saw was the derivative of y divided by the derivative of x. So I'm going to give that the name m for slope. And that's a function of t. So here it is, it's cosine t over 2 cosine 2t. I want to find out what does this function give me when t is pi over 6. So I'll just plug pi over 6 into that function, and what I get is the square root of 3 over 2. That's the slope at that particular point. Now what point are we talking about? I need to put pi over 6 into the x function and into the y function. So I did. X of pi over 6 is square root of 3. Y of pi over 6 is 1. Now to find the tangent line, I'm just going to use the point slope form of the equation. Y value plus slope times x minus the x value. That's what I'm going to do down here. Y value plus slope times x minus the x value. Now I'm going to use a capital X here because little x is already taken. That's our parametric function x of t. So little x is not a variable really, it's that function. So I'm going to use a capital X here just to distinguish between those. So my tangent line is a function of capital X. Sage is case sensitive. So I'm going to now plot the tangent line along with the parametric curve. So here's my parametric plot. Breaks down the line there. that graph's a little hourglass thing, and I can add on a regular plot. So here's the plot of the tangent line, and I've adjusted the window a little bit just so it kind of fits here in the same window with the hourglass. And I added a dot, that's this point command, adding a dot here. This is the point of tangency. So here's my tangent line at that particular point. Looks good. If I were to zoom in right here on this dot, I would see the red and the blue would be very close together. Now that's fine, any of these points along here, until you get around to this point, 0, 0, where it crosses. What happens there? Well, short story is you get two tangent lines. So we need to, in order to figure out what those tangent lines are, we need to know what is t, because our slope is given to us in terms of t. So I know the x and y. 0, 0, I can just look at it and see 0, 0 is where they cross. I want to figure out what values of t result in that point. So I asked Sage, when is x equal to 0 and when is y equal to 0? Solve those for t. And Sage told me t is 0 works for both of them. So when t is 0, I end up at that point. But that's not the only thing. You can see from just looking at these are periodic functions. These are not just 0 one time, they're 0 many times. There is a way to get Sage to tell us additional answers. And in the solve command, you put the equation you want to solve, and then you put the variable to solve for. We're used to that. Now we're going to add a comma and this extra option right here. 2 polysolve equals 4. Now don't worry about what that means or what it does. It's not really important for us, but it will solve these equations and give us more answers. So this is what we get when we ask Sage when is x of t equal to 0. We get t is 1/2 times pi times z45. And when is y equal to 0? T is pi times z50. Now z45 and z50 are just sort of arbitrary variables here. They can be anything. The z means that they're going to be an integer. The 45 and 50, there's nothing special about that. It just puts a number on there just to distinguish them, keep them separate. If I reran this, those numbers would probably change. So you can try that if you want. Just put your cursor here, click run, and these numbers after the z will probably change. You can ignore those. It's the z that matters. Z means integer. So this is pi over 2 times some integer. This is pi times some integer. So in other words, x of t is 0 when t is z times pi over 2 for integer z, which gives us this list of possible t values. Y is 0 when t is an integer times pi, or this list of t values. Now what we want are the t values that show up on both lists. So we're just going to compare this list of t's where x is 0 and this list of t's where y is 0 and see what numbers are on both lists. And it so happens in this particular case that all the numbers on the y list happen to be on the x list as well. So this list of numbers is the answer, where both x and y are 0 at the same time. So z times pi is all those points give us the origin, 0, 0. What's the slope there? Well, I'm just going to try a few values and see what happens. So remember, I have my m function I defined up above, which gives me the slope for any given value of t. So I'm just going to put in an integer times pi for various integers. I'm just going to do -2 to 2 integers there. And what I see is two different slopes, a half and minus a half. And it just goes back and forth, repeats there. So two different slopes means two different tangent lines. Let me get my two tangent lines here. So here's tangent line 1. It's the y value, which happens to be 0, plus the slope. So I'll do a half first, and then x minus the x value. The x value is 0 in this example. Tangent line 2, y value is 0, slope negative a half, x value 0. Notice again I'm using capital X in my tangent line because little x is taken right here as part of those parametric equations. So I'm going to take my parametric plot, I'm going to add a plot of TL1, I'm going to add a plot of TL2, and here's what I get. So if you think of, when t is 0, we get this point, and as t increases, the curve starts going along this way, and the points kind of follow along this path, and they loop around, and they come back here and end up at the beginning. When t loops around this way, going this direction, the slope is minus a half. And when t comes around and is going this way, the slope is positive a half. So you get two different slopes, two different tangent lines, depending on which direction you're going around this curve as t changes.